Good morning, everyone. Welcome back to Satya's Neural Lab. Today, I'm going to go over my project that I did for my machine learning final. So let me start with a story we all know too well, the butterfly effect. And global logistics is not a metaphor. It's daily life. A 20-minute delay in Hong Kong at 3 a.m. becomes a missed flight in Dubai, a late truck in Frankfurt, and a production shutdown in Detroit. And the crazy part about this is most companies only see the problem once it's already exploded. So for this project, I stepped into the role of head of AI at Apex Logistics and asked, can we see this chaos early enough to stop it? So that's a little about the journey I'm taking you on. Here's the headline. I built a model that predicts shipment complexity at 71% accuracy. That's a 7% lift over the baseline model, logistic regression. And that lift translates into a realistic 15 to 20% reduction in expediting fees in this business. But more importantly, this product shows how ML can shift supply chain decision making from reactive firefighting to proactive optimization. That's the real win. Right now, logistics teams all over get blindsided. You can only find out a shipment is in trouble after a critical scan is missed. And at this point, you're out of options, really. Mm, The options would be emergency air freight or customer escalations would occur, and then average $450 more would be added on per shipment. My entire goal was to shift detection left, not after the damage has been done, but before. So how did I go about this? Instead of predicting late or not late, which seemed to me like it was too simplistic, I reframed the problem into three distinct categories of shipment complexity. Class zero, which would be the direct, no transfers, low friction. Class one would be those single stops, where one stop in between, moderate friction. And then class two would be the multi-stop, exponential risk. This is where the high risk target is. If you tell me the structure of the journey, I can probably tell you the failure rate. So the data set I used from this came from the UCI Cargo 2000s ML repository, and it held about 4,000 records. It was small but rich in behaviors. So as for the cleaning part of this, I had to fix missing timestamps, remove 60-day errors, admin errors, and ensure chronological order across all the legs of the journey. So understanding the data set isn't IID, like standard ML homework. In logistics, a delay at leg one causes a delay at leg two. There are dependencies baked into the data that many models really couldn't handle that well. And because of this, I engineered second degree polynomial features. Features such as departure time times route, seasonality times hops, hub efficiency times and route. Because think about it. Let's say you're getting off of work in New York City. If it's just rain, that's all right. But if it's rain and there's heavy traffic, That's where you can really find the most value from this. And this is where ML became really powerful. Models could, with this polynomial features, models could really see the interactions that mattered in the real world. So what I did after I cleaned the data and created those features, I ran a full bake-off of models from logistic regression, random forest, naive Bayes, KNNs, SVM, neural networks, so on and so forth. So as for the naive Bayes, so it assumed that the features were independent, but once again, in logistics, nothing is independent. As for the logistic regression, it stuck at 66% accuracy when I tested it out. This told me the decision boundary is not linear. As for the KNN and SVM, categorical sparsity crushed them, and KNN was pretty much just a guess. And as for the neural network, it actually performed decently, 69% accuracy, but it needed heavy processing and still underperformed compared to the last model I tried. This demonstrated something I learned about in class. Deep learning and neural networks is not automatically better for structured categorical data. And that brings me to the champion, categorical boost or cat boost. Cat boost was built for data sets like this. Reason is its native categorical handling. It processed the airport codes like actual entities, not thousands of one hot vectors. And secondly, it's order boosting. It prevented overfitting by simulating how the model would perform in production. Third thing was it used residual learning. Each tree corrected the mistakes of the last. It made small adjustments like a golf putt until you sink. And then it's also small data set friendly. With only 4,000 rows, this was essential. So after testing about 52 experiments, CatBoost ended with a 71% accuracy score and a 0.70 F1 score, and consistent performance across all classes, which was a key when predicting minority high-risk shipments. So let's just look a little at the scoreboard. So we have logistic regression at 64%, neural network at 69%, and cat boost at 71%. Three things that made it really hard was it's an indirect prediction task. Complexity is a proxy, not the actual delay. And the features really interacted in a non-linear way. As well, the small data set made a lot of these models overfit the risk. Most of these models seem to have memorized the outcome, not really generalized it. But Catboost didn't. So inside this, so I wanted to look at top predictors or SHAP. So the SHAP pretty much told me late origin departures were the most dangerous. More hops in the route increase the risk. And some hubs are congestion traps, probably such as in New York or O'Hare, JFK. The model pretty much behaved like an experienced planner. So After this, I turned this into a decision engine in 3 steps. So class 0 or the direct class will get auto approved. Class 1 would be monitored, and then class 2 would be manual review. By automating the low risk shipments, I focused human experts solely on the top 20%, preventing expensive expediting fees. It wasn't full automation, but it was smart automation. So after this, after we did all this, I took this model out of the notebook so people could actually see how this was built. I created a Streamlit app so planners can actually use it. So now I'll move into the web app. So just to give you a little background, this was my whole Python code for creating the models. Installed all the dependencies, imported, configured Databricks because all this was logged onto Databricks, MLflow. We loaded our CSV file, created this polynomial features, created the models and the different hyperparameters for each model. Then we ran the models. And so now we have this. This was the actual experiment. Took me 6 attempts to get this all right, but it is. And we see right here, I've sorted them from F1 score macro. Cat boost default was the best. From there, I served this, published this model, and then created the app.py. And pretty much this app.py creates this. So we have our interface, we have the on-time performance, high-risk shipments, average transit time, active shipments for today, active shipments. We have network status, and down here is where we really do it. So we have total journey legs. Let's say we'll do 3 journey legs. And we'll start from facility 100 to facility 815 and generate risk assessment. High risk, 100% probability. We also have the executive view, which just shows shipment flow distribution. And I added a night mode and day mode feature to it. So here's the full ML pipeline from data ingestion, cleaning, feature engineering, Databricks training, ML flow, tracking to the streamlet. This mirrors a professional production ready workflow. Python, Cat Boost, ML flow, streamlet, and all the dependencies were logged. And before I put it on Streamlit, I put it on Ngrok just to see if it worked. I also use Google Colab to start with this, and then from there uploaded that to my repos in GitHub. And to wrap up, I built a 71% accurate risk classifier that outperformed linear and neural baselines, deployed an actual interface, and shifted from reactive firefighting to proactive strategy. The next steps would be to integrate the web app with said business. From there, after quarter 1, integrate weather APIs, integrate their whole shipment. Maybe they start out with just a city or just state, but the next step would be that. And finally, the last step I thought of was to scale to ocean freight. And lastly, here's all the technical backup just to show the dependencies listed, my hyperparameter for my cat boost ensemble, my data dictionary, and my confusion matrix for it. Thank you. If you like this, please subscribe and hope you have a wonderful day.